Hello, here is our second project for MSE 2001 on water contact angles. This is just our table of contents. The two materials that we used for our experiments were 100% nylon 2-layer and low-density polyurethane, with the former just being a rain jacket and the latter being a plastic Tupperware. Due to some prior knowledge about what these materials might be used for, as well as how the surface felt and how the water clung to the surface, we assumed that material 1 was likely hydrophobic, the rain jacket, and that material 2, the plastic Tupperware, was likely hydrophilic. Here are some results from experiment 1 that prove our hypothesis is true. Material 1 has an average contact angle of 119.3, which is larger than 90 degrees, and material 2 has an average contact angle of 61.65, which is smaller than 90 degrees. Because material 1 has a higher contact angle than 90 degrees, we can assume that there's less adhesion between the water and the rain jacket. This also means that the bonds between them are weaker. The molecules aren't attracted to each other, so we can assume that the rain jacket is hydrophobic. The opposite is true for material 2, where the contact angle is less than 90 degrees. We can assume that there is more adhesion and that the bonds between the water and the plastic Tupperware are stronger, that there's more attraction between them. This makes us believe that the plastic Tupperware is likely hydrophilic. We know this because water is a polar molecule, which means it's attracted to other polar molecules. Due to uneven charge distribution, one side of the molecule is negative and the other is positive, allowing them to link together like magnets are able to. This isn't true for non-polar molecules like the ones we find in material 1. Because they have an even charge distribution, there's nothing for the polar molecules in water to be attracted to. Unfortunately, with experiment 2, we weren't really able to confirm our hypothesis. A smaller roll-off or sliding angle would mean that the water droplets were able to move off of the material more freely. Being able to move more easily would point to less adhesion and less attraction, which would represent a hydrophobic material. Of course, the opposite would be true for a hydrophilic material, which would need a higher roll-off or sliding angle to prove that there is more attraction and more adhesion. Our results don't demonstrate this, as material 1, which we hypothesized as hydrophobic, actually has a higher roll-off or sliding angle than material 2, which we assumed to be hydrophilic. We anticipate that there might have been some error in the way that we dropped the water onto the materials, which led to some confusing results. There are actually a ton of real-world applications for both hydrophilic and hydrophobic materials. Hydrophobic materials are really good for inventions or projects that you don't want to get wet. This could be anything from a rain jacket, which is meant to keep you dry, medical implants inside of the body, which have components that you don't want to get wet or grimy, self-cleaning materials, things that sit outside for a long time and you need to have them be kept dry, like solar panels, or any water collection system. Hydrophilic materials are good for projects that you anticipate to get wet or want to absorb water. This could be anything from towels, which obviously you want to be able to absorb water in order to keep you dry, medical devices that travel through wet areas of the body, like catheters that you might want to keep from getting damaged by various liquids, and filtration devices, which can obviously absorb water and then spit back out something cleaner. And that concludes our project. Thank you so much for watching.